There are two types of accelerometer calibration that we applied as initial accelerometer calibration, which is provided by the factory in accordance with the Australian standards. These accelerometer calibrations are conducted with respect to a laser vibrometer, which provides the vibration reference, and this can be found out, more can be found out about this in the Australian standard. However, the second type of accelerometer calibration is the one that's conducted prior to making a measurement, and for this it's a reference accelerometer measurement. Typically we would either do this using an accelerometer calibrator, which is a handheld device, or, as is shown in this slide, we can use any shaker to generate a relatively unknown level of acceleration, and we use a reference accelerometer, which is, for example, a new accelerometer, and we compare our unknown accelerometer, the one that we want to calibrate, in terms of its output with respect to this reference accelerometer. So this is a relative reference measurement, and it enables us to have a traceable calibration with respect to the reference accelerometer that may have recently been purchased and calibrated by the factory. Our unknown accelerometer may be one that's been in our collection of accelerometers for several years. This is often cheaper to do this, i.e. buy a new accelerometer, than it is to send our old accelerometer back for a calibration with NATA approved accelerometer calibrator supplier. Another type of accelerometer calibration which can be applied is one where we use a laser vibrometer to do a dynamic calibration. So previously we would have done similarly, that's a dynamic calibration, but typically at a fixed frequency, maybe 159.2 Hz, which is a convenient frequency, a single sinusoidal frequency component. In this case, we could apply with our electrodynamic shaker a broadband acceleration, and we can make a measurement of that broadband vibration signal using both the accelerometers which are being calibrated and are attached to the electrodynamic shaker, as can be seen in this image, and comparing that with a vibration velocity signal that's collected by the laser vibrometer, which is attached above those accelerometers, and makes a measurement from the top of the accelerometer in the same direction as the accelerometer sensitivity. We can integrate the velocity signal in the frequency domain relatively conveniently, and then compare and contrast that to the accelerometer measurements. We differentiate the velocity signal and compare that to the accelerometer measurements in the frequency domain, and then we get a calibration or a sensitivity value which we can update into our data acquisition system such that we get calibrated measurements with our accelerometer. An alternative type of calibration that is relevant for a sensor which has a DC response, i.e. a piezoresistive accelerometer or a MEMS accelerometer, is simply to put the accelerometer on the table in the lab and then make a measurement of acceleration due to gravity. And if we then invert that accelerometer, i.e. turn it upside down through 180 degrees, whereas previously it would have been measuring 1G, it would subsequently be measuring minus 1G because it would effectively be upside down. That's a 2G difference, and that will give us a different voltage output. We can then calibrate that voltage output by dividing by 2G, and we get a relative calibration or a calibration for the sensor. A fundamental requirement of all vibration transducers is that they have a flat frequency response across the range of frequencies that they are used for. This is because if we want to have a reliable measurement, it's no good to us if we have a resonant frequency at, say, 2 kilohertz, where we're making vibration measurements such that our output from our vibration transducer is amplified at that resonant frequency. So if you look at an ideal response for an accelerometer, this is a single degree of freedom system on the right hand side of these two plots. You can see that it's very flat up to around about 10 kilohertz. This is a log scale on the x-axis. And then we start to approach the resonant frequency, which is around about 40 kilohertz for this case. So we would really typically only use this accelerometer up to about 10 kilohertz, where it's got a flat frequency response. That's an ideal scenario. If you look at the individual frequency response for a particular sensor, that's shown on the left hand of these two plots, and you can see that we do get some small amount of deviation in sensitivity. This is a percentage value, so it's only around about 1-2% as the frequency increases between 5 Hz and, say, for example, up to 5 kilohertz. These dotted lines in these two plots also show the phase response, and so the phase response is also important. It's no use to us if we have signal that varies in phase, i.e. it's retarded or advanced with respect to the actual vibration. So we ideally need a flat phase response in frequency as well as amplitude response. Piezoresistive accelerometers are typically used at lower frequencies than those piezoelectric accelerometers. So whereas previously we were looking at up to 10 kHz frequency response for a piezoelectric accelerometer, here we typically would be only good for up to 500 Hz or 1 kHz for a piezoresistive accelerometer. They do, however, make measurements all the way down to DC. In this case, we only show measurements down to 1 Hz on the left-hand side. These are typical frequency responses rather than individual frequency responses. So this is just for a range of sensors. And you can see that the ranges give us very different or alternative sensitivities. These can be readily programmed into the same accelerometer, essentially just by changing the electronics slightly within the amplification for the transducer itself. Because we have such wide-ranging values for vibration amplitude when we're dealing with vibration measurements, not least because as we approach resonances we get significant increases, it's not convenient to use a linear scale for the representation or the presentation of vibration on the y-axis. So we typically use decibels or log scale. Decibel is just one form of log scale where we specify a reference for sound pressure, for example, for the measurement of hearing, or using microphones, that threshold or that reference power would be the threshold of hearing, which is 20 micropascals. In a case of vibration, we would typically use, for example, 1G or 1 meter per second squared as our reference for the decibel calculation, which is done either from a power standpoint by taking 10 log 10 of the power ratio, i.e. the measured power relative to the reference power, or for an amplitude measurement it would be 20 log 10 multiplied by the voltage ratio, i.e. the measured voltage divided by the reference voltage. So just to put the measurement of decibels into some more context here, you can see the equation of decibel measurement for voltage, which is 20 log 10, as in the log 10 rather than natural log or log base 2. This is a base 10 logarithmic function of the measured voltage divided by the reference voltage. For power measurements, we describe a different equation. So since power is essentially velocity squared, then we actually, in this case, calculate 10 log 10, the power divided by the power reference. For vibration velocity decibels, we would typically take, for example, a voltage reference, a velocity reference of 1 nanometer per second, and we would divide the measured velocity by that reference. Again, we would calculate decibels by 20 log 10 multiplier of velocity measured over the velocity reference. And for acceleration, here we can see that the reference actually is specified as being 1 micrometer per second squared, so A0 is 1 micrometer per second squared, and the measured acceleration is divided by that, and then we take 20 log 10 of that to get a measurement in decibels. So using decibels to describe the sensitivity of a transducer, you can hopefully clearly see that if our nominal sensitivity for the sensor is 4 millivolts per G, and we have an actual sensitivity at, say, 1 kilohertz of 4 millivolts per G, then 4 over 4 is 1, and log 10 of 1 is 0, so we get 0 dB. So if the sensitivity is completely flat across the entire frequency range, we essentially have 0 dB, a straight line along the frequency range at 0 dB. As mentioned before, this is a single degree of freedom system, so it has a natural frequency. The piezoelectric element is pretty stiff, so those natural frequencies are generally high. And in this case, we've got a peak at around about 40 kilohertz of 30 dB. Okay, so as we approach that 30 dB, we actually get more volts out of the sensor for a given amount of acceleration because it likes to move at that vibration frequency. 30 dB, essentially, if you do the calculation backwards, you can see that that leads to effectively a sensitivity of 126.5 millivolts per G. So if we excite the sensor at 40 millivolts per G, we get lots of response. We therefore get lots of compression of the element and we get lots of voltage. So that makes sense. This is why we use dBs to present sensitivities in this way, because for a 4 millivolt per G flat line at 0 dB, we would be getting actual sensitivity equal to the nominal sensitivity. dBs are often also used to describe the gains of amplifiers. So when we have low-level signals, we typically would amplify them to make them more obvious or of larger levels, such that they can be captured more effectively with reduced, ideally with reduced noise levels relative to the given signal. An amplifier, for example, with a gain of 1,000, we would describe that in terms of its dB amplification by calculating the output voltage over the input voltage. So a gain of 1,000 means that we'll have 1,000 times output voltage with respect to the input voltage. Therefore, the calculation of gain is 20 log 10 1000. If you put those numbers into the calculator, you'll soon see that 1,000 gain is equivalent to a 60 dB increase in the signal level. Note that for a gain of 1, i.e. the same input voltage as output voltage, i.e. there's no gain, essentially we get 0 dB. Decibels are also useful to describe the performance of filters. If a filter is applied, that leads to a reduction in the output voltage with respect to the input voltage. A quick example of that would be, for example, if we were to reduce the output voltage by a factor of 2, i.e. the ratio of output voltage to input voltage would be 0.5, then that is equivalent to a minus 6 dB reduction in the output voltage. In the case of a filter, we talk about a cutoff frequency. So as I mentioned previously, analog filters do not perform with an instantaneous cutoff frequency. They have a roll-off that occurs over a relatively wide frequency range. We talk about the cutoff frequency as being the point at which we get a 3 dB reduction in the signal level. At this point in the class, we'll do an in-class exercise. At this point in the in-class lecture, there will be a demonstration.